In this video, I would like to give you two proofs of the existence of infinitely many primes. This is a very fundamental basic fact in number theory. And the first proof is due to Euclides. It's the oldest known proof of this fact. And it's very beautiful and elegant. So the proof goes as follows. Suppose that we have only finitely many prime numbers. This is P1 up to Pk here. And so we suppose that there are finitely many of them, and they're all listed therefore in this list. All of them are here, finitely many of them. And now what we will do, we will consider the following number n, which is the product of P1 all the way up to Pk. So we take the product of all those numbers and we add 1 here. And the reason for this 1 will be clear shortly. And so let's see. So if this number n that we have constructed here is a prime, then it means that we have arrived at a contradiction, because this number n is clearly bigger than all the numbers in this list, so it's not on this list. And therefore, if n is a prime, we found a prime which is not on the list, which is a contradiction because we assume there are finitely many and we listed them all. So n is not a prime. Where's the contradiction here? So here we need to invoke the fundamental theorem of arithmetics that says that every number is either a prime or divisible by a prime. Therefore, if those are all the primes in existence, and there are finitely many of them, and they're all on this list, right, then n must be divisible by at least one of those primes. But when we divide n by any of those numbers, it is easily seen that n leaves a remainder of 1 when divided by any of those numbers. And therefore, it's again a contradiction. It's a contradiction that stemmed from our assumption that there are only finitely many primes. And as a result, we are inevitably led to the conclusion there are infinitely many primes. And this proof is so beautiful and so elegant of a non-trivial fact. And a mathematician, famous mathematician, Paul Erdos, said this proof of Euclides is a proof from the book. Now, what did he mean by a proof from the book? So, Paul Erdos said jokingly that God must have this book that contains all the theorems in mathematics with all the proofs. And all the proofs to those theorems are the most elegant, most beautiful, most ingenious, most straightforward, most clever, most everything. And so when he referred to this theorem of due to Euclides to this proof, he said this is a proof from the book. And in fact, now there is actually an interesting book, and you can find the link in the description below to this book. And this book is called Proofs from the Book. So the author of this book assembled a list of really interesting theorems in mathematics with really elegant proofs, and in the author's opinion, those proofs deserve to be in the book. They are that great, they are that brilliant. And so I really recommend you check the link in the description, and I would really recommend you even to buy this book, because this book does an honor on the shelf of every mathematician. I have this book, and it's beautiful and it's wonderful, so I would recommend that you buy it, or at least check the link for it. And now I would like to tell you another proof due to Euler. And Euler derived another proof for the fact that there are infinitely many primes, but this proof due to Euler has its own merit, but it is technically more involved, and you really need to know more mathematics to understand it. It's not that elementary. So let's see what was Euler's proof. So again, Euler assumed, just like Euclides, that suppose that there are only finitely many primes, P1 up to Pk, and that all the primes are in this list. Now, consider those series. 1 over P1 to the power of L1, where L1 goes from 0 to infinity. Now, this is those are a convergent geometric series, and therefore it converges and it has finite sum, and its sum is 1 over P1. And we can do it with all the primes here. There are finitely many of them. So we can construct those series. Lk here goes from 0 to infinity, 1 over Pk to the power of Lk, just the name of the index here, and the sum of those series will be 1 over 1 minus, let's call it P k to the power of minus 1. Let's call it this way. And here we could call this 1 over 1 minus p1 to the power of minus 1. And okay, so we have finitely many primes here. And so what we can do here, those series that we have here are positive convergent series. And as a result, those series are absolutely convergent. And there is a theorem that says that we can multiply those series. So if we take all those series, 1 over p1 to the power of L1, L1 goes from 0 to infinity, and we multiply this sum, and we multiply it sum of 1 over, let's call it p2 to the power of L2, L2 goes from 0 to infinity, and we have, eventually we have a finite product here, and we multiply it, here we have 1 over pk to the power of lk, as lk goes from 0 to infinity. So this is a finite product, and in fact this product we could write it if we wish as product of 1 over 1 minus p, let's call it pi to the power of minus 1, as I goes from 1 to k, runs over all the prime numbers. This is on the one hand. On the other hand, the theorem says that we can take the product of all each. It's proved for two series that when you have absolutely convergent series, then you can basically multiply them term by term and sum over all the possible terms, and this will be, the sum will converge to the product of the sums. This is for absolutely convergent series, and the result of the sum is independent of the order of summation. It seems obvious, but it's not that obvious. It's not true for series that are conditionally convergent. So check this out. But for absolutely convergent series, as positive series that we have here, the product of those series is, in fact, we need to sum over all the values L1 up to Lk as they go from 0 to infinity, and the general term here will be p1 to the power of L1 up to pk to the power of Lk. And we need to sum over all the possibilities of L1 up to Lk. Okay, and so where's the contradiction, you ask? And here again, we also need to invoke the fundamental theorem of arithmetics that says that any natural number can be written as a product of primes which is unique up to the order of the factors. And as a result, since those are positive convergent series, then their order of summation, the sum is independent of the order of summation, and in fact it has to be equal to the sum as n goes from 1 to infinity of 1 over n. And so let's see what we got here. We got here that the sum of the harmonic series, if there are finitely many primes, has to be equal to this finite product, right? Of finitely many, we have finitely many primes, then this is just, this product is a finite number, and therefore the harmonic series are convergent. But we know that the harmonic series are divergent, and this is a contradiction. And this contradiction arises exactly because we assume that there are only finitely many primes. And so this proof is due to Euler. And well, it's really seems, how did he come up with it? Well, and the reason is that he was studying the Euler zeta function, which was then extended by Riemann. And the Euler zeta function is the sum of 1 over n to the power of s, and goes from 1 to infinity, and then for every s that is greater than 1, those series are convergent, for, let's suppose that s is real. And then the work of Riemann actually allowed to extend zeta to the complex plane and define, give a meaning, to assign a meaning for every complex s here, except s equals to 1, then, there's a meaning to this series. So, and then Euler proved the Euler formula, that in fact this sum can be written as the following product, as p runs over all the primes, and here we have 1 over 1 minus p to the power of minus s. And this is an important product formula, and this is the importance of the Riemann zeta function because of this relation of zeta to the prime numbers. And so here, if we look at those series and we plug in s equals to 1, right, then here we would have this product of 1 minus, let's just plug it in. So this product of p runs over p, and here we would have 1 over p to the power of minus 1. But this is in fact the product of p over p and of the sum of the following form, 1 over p to the power of k, as k goes from 0 to infinity, right? We just basically do it for every prime. This is on the one hand. And on the other hand, if this set of all the primes is finite, then this is finite. But on the other hand, this has to be equal to n goes from 1 to infinity of 1 over n, and those are the harmonic series, and they're divergent, so this is infinity. And so as a result, I'm almost sure that that's the way that Euler came up with this proof. So thank you for watching, and if this video gets at least 100 likes, I promise that I will do a playlist dedicated to the Riemann zeta function. So thank you for watching. Please consider subscribing to my channel and click the bell button not to miss future uploads. Thank you.